streaming now. So hello everyone, I'm Maura Pintor and I'm a postdoc researcher at University of Cagliari. Welcome to a new event of our machine learning seminar series. Back from the vacations in summer, we have today Maksym, who will give an amazing talk about adversarial attacks on image attribution. Right before we start, I would like to give you some additional information about the seminars. First, the event is live streamed and recorded. So if you don't want to be recorded, then feel free to follow from YouTube. About the questions, we will have time for questions at the end of the talk. And we will prioritize first the Zoom call people. So people who raise the hand, and they will have the chance to talk, to ask questions. Then we go to the Zoom chat, and if there's time left and more questions, we can go on the YouTube chat. That is also live. For knowing more about our seminars, you can follow us on Twitter, LinkedIn, Eventbrite, on all the links that I will send in the chat very soon. Finally, if you're interested in learning more about machine learning security, or you feel like you want to strengthen your background for following our seminars, check out the course that we have on the same YouTube channel where we live stream this service, and you will find a good course on adversarial machine learning there. That is, of course, free. Now, I just want to thank all people who helped me organize the seminar, and I'll give you the stage, Luca, so you can introduce the speaker for today.
Really, thank you, Maura. So today we have Maksym Andriushchenko. She's a third-year PhD student in computer science at EPFL in Switzerland. And he obtained his master's degree from Saarland University in Germany, and he is currently now researching how to make machine learning more robust to adversarial attacks, and how to improve their reliability. And Maksym also published already a lot of papers in top-tier conferences, including NeRIPS, ICML, ICLR, CVPR, just to mention a few. So without further or any other discuss, I'll leave you the stage to you, Maksym. Thank you again for being here.
Okay, hello everyone. So thanks a lot for a very nice introduction, and thanks a lot for coming. And okay, I first of all, I must say that I'm really excited to give a talk here in this lab, because the lab of Batista, right? It was like one of the first. I mean, Batista was one of the pioneers of adversarial machine learning, right? And recently got the Test Time Award at ICML, right, for his work 10 years ago. So yeah, it's really nice to be here. Okay, so I will share my slides. Just give me a moment. Okay, I hope you can see it. Yeah. Okay, so the topic of okay, before we start, yeah, I would like to say that questions are welcome. So if you have some questions about, like, if something is not clear, or if you want to ask something, then feel free to interrupt and raise your hand. And yeah, so I would like to, like, if we handle the questions during the presentation, or and also after. So basically both work, options work. Okay, so basically the topic of this presentation will be our paper that we published at the CVPR workshop this year. So the workshop is on media forensics, right? So okay, so let's try to understand what it means. So the paper title is ARIA, Adversarial Robust Image Attribution for Content Provenance. So it's basically, okay, so the general task is, okay, so the general goal is how to make internet more trustworthy by attributing the content to the right source. Right? Okay, I will explain it in more detail, but I think this goal is quite important. So I must say that this is a joint work with Adobe. So I was an intern at Adobe Research, and also with our collaborators from, obviously EPFL, where I'm doing my PhD, and the University of Surrey. So yeah, but okay, before we talk about content provenance, let's discuss a little bit about adversarial vulnerability in general in deep learning. So I'm sure that many people here probably know very well about adversarial vulnerability and this problem, but let's just make sure that we are all on the same page. So what is the problem? The problem is that small perturbations of the input data can cause a misclassification with a high confidence, right? So this is illustrated usually by this picture that essentially we have this nice picture of panda, and we have some classifier which says that with confidence 57.7%, it is panda, so it's a correct prediction. And then if we add some imperceptible noise, which looks in a completely unstructured way, suddenly the model says that actually now it's a gibbon with confidence 99%, right? So it completely changes its decision, although there are no features of gibbon in this class, right? So this has been known for quite a long time. So I'm citing here actually a paper of Goodfellow, but I know that that Batista did it before. So yeah, I should be careful about that. So this is nonetheless, if you don't talk about the right attribution of who did it first, in any case, it's a real problem, and we should think about how we handle it. So why it is important? So I think for me, I would say that three things are the most important here. First, it's a question of interpretability, right? So interpretability and also trust of the model, right? Because like if the model can change its decision so dramatically, it means that we cannot trust the model, right? So it's a black box that that fails. And then how can we deploy these models for something like self-driving cars and other safety critical applications, right? The second concern is more about understanding these models and understanding their out of distribution generalization, right? So basically this kind of small worst case perturbations are kind of extreme case of out of distribution of a distribution shift, right? Where each image is shifted by a little bit, but in a worst case such that the model completely breaks, right? Again, it's a question of trust to the model, right? So because like there will be always some distribution shifts at test time, at least because we always deploy the model, in the future, and we always train it on the past data. So yeah, so it's a fundamental question. And the third question, and this will be the main topic of this talk, is about security, right? So it's basically, so this vulnerability means that the attacker can manipulate the decisions of the classifier and potentially avoid, let's say, manipulate the decision in such a way that benefits the attacker, right? And this is really concerning. And I would argue throughout this talk that for content provenance, it is especially an important security problem. Okay, so let me quickly check the chat. Okay, perfect. Okay, so no questions, but feel free also to write your questions in the chat or raise your hand or whatever is more convenient for you. Okay, so now a little bit more about the task of image attribution for content provenance. So there is an initiative which is called Content Authenticity Initiative, which is led by Adobe, but it also involves a lot of different companies and NGOs. So kind of the goal of this initiative is to authenticate original images using either metadata or deep image fingerprinting models. Okay, so what it means to authenticate original images, we know that now there are multiple ways how we can create deepfakes, right? Or just fake images in general, right? It might not include deep learning necessarily, right? So it could be some other modifications, right? But now we can do it using, for example, Photoshop, right? Or we can use, all these fancy new models like DALL-E and so on, right? To generate, or even Stable Diffusion, which is now completely open source. So we can create a lot of fake content, right? Some personalities that never existed and so on, right? So it's kind of the technological advancements on this front. They also mean quite significant potential for disinformation, right? And this project aims to fight disinformation by making sure that we can authenticate and say which images are original and which are not, right? And essentially, this can be done in two main ways. So using either metadata, right? But this is not always feasible because if you just look at the metadata of the image, then sometimes like some social networks or news websites, they completely remove metadata. So it's not always a feasible solution. Or alternatively, you can use deep image fingerprinting models in order to find the original images in the database and then also visualize the editorial changes. So I will show you a diagram how it looks like. So for example, like now I will describe the pipeline, which is coming from this paper last year, which is from Adobe Research. Essentially, how it works is in the following way. So imagine that you have some original image. For example, these are, let's say, two soldiers, right? And then you want to change the content of the image, right? So you want to manipulate it in some way, which is potentially like, so you want, let's say, to spread disinformation, right? And then you change the one of the objects on the image, right? And this is now it's very easy to do using tools like there are a lot of tools to do this, right? So and you can do it in a completely realistic way, such that okay, I would, it would not be obvious for me that this object has been photoshopped, right? But you know, you can you can produce very high quality fake images, right? So and then what you can do, you can also add an imperceptible adversarial perturbation to this fake image in such a way that when this image is distributed online, right? So for example, like on Twitter or on other sources, then if we use this image attribution pipeline, we map this image to a wrong source or original image, right? So essentially what happens is that, okay, we find a closest match in the database. So we assume that we have a large database of original images. So imagine something like, I don't know, Google image search, something on this scale. So basically for a non-robust model, the adversarial perturbation which is added to this image would lead the model to match it with some arbitrary image, right? But if you have a robust model, and this is an illustration from our model that I will describe, we have essentially we have the original image like before this editorial changes, right? Before changing this object. So we map it to the original image, and then we can highlight where the most likely change has occurred, right? So essentially, so here we can like the last image corresponds to a heat map, which says, okay, that in this part of the image, it is likely that there has been some photoshopped changes, right? Some editorial changes. Okay, so this is the pipeline. Okay, so it is fairly complex, right? So it's not like a standard model on Cypher10 where it's just a single network and then you classify 10 classes, cat, dog, right? So it's really more complex, but I think it's interesting also to look at this kind of problems because I think most of the models that are actually used in practice, they have multiple stages, right? And then if you consider the problem of adversarial vulnerability and attacks on these models, then this is also a multi, then you have to make sure that you fool the whole pipeline and not just separate parts, right? So it's more of an engineering challenge, but I think it's a very interesting one. Okay, and okay, so the first contribution that we make in this regard is that we demonstrate that image attribution models of this kind, right? So this kind of two parts procedure where we first do image attribution and then we do heat map visualization of the changes, it is vulnerable to realistic adversarial attacks, right? So this is the first part, right? And then let's try to understand a bit from the technical side what happens, right? So basically on the technical side, we have a fingerprinting model, right? So essentially which computes some image fingerprint, which is essentially, it could be either just a feature vector, or it could be a feature vector which is, let's say, binarized. So it's a hash to enable more scalable search. So both options are possible. And the goal of the attacker is to add an input delta, right? So an input change delta such that the fingerprint of f of x plus delta is far from the fingerprint of the original model of the original image, which is stored in the database, right? And we also need to make sure that the change delta is small, so that the change is imperceptible, and the attacker can so that it's not clear to the user, let's say to the person on Twitter, that this image has been manipulated in some adversarial way. Right? So this is important. And the result, so one possible result of the attack is wrong retrieval. So that essentially a wrong image is retrieved from the database. And so why it's a meaningful attack model? Because in this case, we cannot trace the original image. So we cannot map the test time image to the original one, even though it is in the database, right? So we know that, okay, we have indexed this image, so we know that, okay, this image is original, right? But we cannot really, so basically our pipeline fails as if we did not have this image, right? So this is potentially, this is a mistake, right? And this is potentially could be harmful. So how it works is that essentially, okay, so we have a query, right? So it basically has both editorial change, right? So this object is different, right? And also an adversarial attack, right? So just maybe you can see in the background there are some very small artifacts, right? Which corresponds to the adversarial attack. And then if you have an undefined model, then the closest matches that the model returns are the following. So it's completely irrelevant images, and even if we consider like top 3 output, or even top 100, there's no original image in the retrieval. Okay. So why it is a realistic threat model? In our opinion, because adversarial images are provided directly in a digital format, right? So there has been a lot of literature on crafting realistic adversarial examples, right? Where realistic usually means that they have a lot of requirements. Well, I shouldn't say realistic, I should say like real world adversarial examples, right? So I think that's how they are usually called. When an usual example is something like a stop sign, like a sticker on a stop sign, so that you want to fool, let's say, a self-driving car, like from different angles and from different scales, right? So there it's much harder, and I think it's barely possible. But in this case, in case of model that operates completely on images, right, and does not have kind of a real world component, right? So it's not like we are going with the camera and taking photos from somewhere, right? So we are really processing directly JPEG images, right? So essentially, the only requirement is that the adversarial perturbation should survive JPEG compression scheme, right? So like after the adversarial perturbation should be such that after applying JPEG compression, it is still adversarial, right? So this is essentially the only requirement in this case for the attack to be realistic, right? Okay. Then we also assume white box setting. Okay, so why it makes sense here? So basically we have two main options, right? Either white box or black box setting in terms of the knowledge of the model, right? And the important part is that here, according to the content of the TCT initiative, this model phi of x is potentially going to be deployed on edge devices, right? So which basically means that it is not on some secret server. It is delivered on edge devices, and then everyone can essentially reverse engineer it. So we should not assume that this is just a black box, and the only thing that we can do is black box adversarial examples, right? So this is another important point which motivates or kind of defines our threat model. And and essentially what we argue is that such vulnerability is very concerning, since essentially malicious users can bypass this content authenticity model and spread inauthentic content, right? So, and this is particularly concerning because now we have a lot of repositories online, right? So like there are a lot of libraries to generate adversarial examples. So now it's just really like one line, right? So you can use for example, also the library from the group of Batista, right? So like there are a lot of them, right? So it's really easy to use, and it's really easy to craft, especially white box adversarial examples, right? So this is really, I think, an important security problem. Okay, so now a little bit more about technical. Okay, so how do we generate adversarial attacks on these models? So okay, so again, the goal of the attack is to add a small perturbation delta such that the embedding of or fingerprint of x plus delta is far from the original image, right? So this is essentially the goal, and we can formulate it in the following way. So okay, so it's not a new formulation. So it's like there have been definitely papers before that try to do this, but mostly in the context of image classification. So I think image attribution, or yeah, essentially I think image attribution is much less explored compared to image classification. So, but the only change compared to image classification is the objective itself, that instead of producing a misclassification, instead of maximizing the loss with some label y, what we do is we maximize the L2 distance between x plus delta and between the embedding of x plus delta and the embedding of x original. And we have the two constraints on delta. So the first one is that in terms of the L infinity norm, it should be not greater than epsilon. And second is that x plus delta should be still a valid image, so that it's from 0 to 1. And this objective can be reliably solved via projective gradient descent. So okay, so what means reliably is has to be maybe more clearly defined, but at least in most cases, let's say in most cases, running a simple algorithm like projective gradient descent gives you near to optimal adversarial examples. Although I must say that there have been a lot of work on how we can improve the adversarial examples given by this method, but I will not go into those details. Okay, so and essentially, if you have fingerprinting, so essentially, if our embedding f is discrete or if it's binary, so for some applications, if you want to enable scalable search, you want to have binary embedding, right? So let's say either zeros or 1. Then this can be handled via differentiable approximation of this thresholding function. So it's not a problem in practice, and in the paper we have some experiments with it. Okay, so and yeah, so what we found is actually that even this kind of naive attacks where we maximize just the L2 distance between the embeddings, typically it preserves very well the effectiveness under moderate JPEG compressions, right? So we didn't even need to use any differentiable approximation of JPEG compression for generating adversarial examples, right? So which was kind of quite surprising for us, because we thought that probably JPEG compression removes the adversarial examples to some extent, right? But actually it's not the case for moderate JPEG compression. So basically, like standard adversarial examples usually survive it quite well. Okay, so this was about the attack part, right? And now about robust contrastive learning for this image attribution task. So okay, so I hope the notation is not too heavy. So if we so I must say that that for image attribution models, usually one trains them in a contrastive way, using a contrastive learning objective of the following kind. So we minimize over our parameters, over the parameters of the network. We minimize the expectation over batches of size 2n, right? So we sample these batches from the data generating distribution D, and we minimize the contrastive loss L. For example, if we take the SIM-CLR loss, okay, so the SIM-CLR loss is coming from this paper, a simple framework for contrastive learning of visual representations from 2020. So I think now it's probably one of the most standard ways how to train contrastive learning, both for if you want to improve your like both for pre-training, right? So basically to get as good as possible in terms of transfer learning, or also if you care about tasks like image attribution. Okay, so the loss is basically given here. So okay, so it's a bit complicated, maybe a bit counterintuitive if you see it for the first time, but okay, I'll explain like the idea behind it, right? So the idea is that you want to have the different augmentations of the same image. So okay, so here it is assumed that the images are paired in this batch of size 2n. That basically that you have paired images, that the first image and n plus first image are just different augmentations of the same image, right? And then you want the embeddings of the same image to be close in this embedding space, and the embeddings of different images to be far, right? So this is the essence of this of the SimCLR loss. And yeah, and apparently this precise loss is somehow optimal or close to optimal to give you a good embedding space where you have this property of distance, so that you can use just L2 distance in embedding space to do essentially this image attribution or other tasks. So what we propose to do is to essentially to add the maximization problem for over the perturbations delta here. So okay, so what happens here is that okay, so instead of minimizing the expectation over the batch, we add kind of an independent perturbation delta I for each image in our batch, right? And then we just maximize the overall loss of this SimCLR objective, right? So this is the formulation. So it is of course very much inspired by standard adversarial training. I mean, this is a way to do adversarial training or robust optimization for this kind of contrastive learning loss, right? So, but it's much less explored in the literature compared to image classification, right? So, so basically, what we do in essentially in practical terms, we use adversarial training like on this objective, right? On this SimCLR objective, and we solve the maximization problem with a few iterations of projective gradient ascent. So it is fast in practice. So in practice, we get at most 2 times overhead compared to standard training, right? So it's still feasible for large scale training, which is quite nice. And this is the first point. And the second, yeah, okay. So about the interpretation of this process, I mean, so yeah, so essentially this maximization procedure inside of the expectation, it has kind of a nice interpretation in terms of that. The adversary here, I mean, the adversary is essentially the process that tries to solve this maximization problem, tries to do the opposite of what we want from this SimCLR loss, right? SimCLR loss tries to pull together the same, like the images that are the same, right? That are coming just from different augmentations. And instead, the adversary tries to add perturbations in such a way that they are far away from each other, right? So, and essentially, yes, it kind of totally makes sense from the kind of from what we want ideally from the adversary to do. Okay, I hope this slide was not too heavy. So okay, so now about the main results. Okay, so now like about the performance metrics. So we measure both top 1 recall and top 100 recall for this model. So essentially, top 1 recall means that okay, we retrieve only one image, which is the nearest image in the embedding space, right? And we say, okay, this is probably like this is the closest match. So that's why probably this is the original image corresponding to the test time image that we get, right? So, and recall at 100 is top 100 recall. So basically check whether the original image is contained in the top 100 retrieval from the model, okay? And the important point is that we evaluate on adversarial examples with epsilon 8 or 255. So of course, it's like, yeah, it's a big question about what we want in practice, like what kind of robustness until which point we want, right? So in our case, we followed essentially the literature on adversarial examples in image classification, and there it's a standard threshold. I think it kind of makes sense also in general, right? So basically what we observe is that for this threshold, we don't have significant degradation of the essentially of standard recall, right? So, okay, so I will show you the results, and yeah, so I think this is probably a good, like relatively good threshold. Although, of course, it's a kind of a design decision about how much robustness do we want, right? So, and then we evaluate on adversarial examples, but only after we save them as valid JPEG files, right? So this is important to make the attack realistic, right? So that we are dealing like with an attack which can be really run kind of in the wild, right? So and in the wild you have essentially JPEG files which are distributed, you know, on some social media websites and news websites and so on. Okay, so these are the existing models. Okay, so the table has a lot of columns. So let's try to understand what is here. So okay, so first of all, on like there's R1, R at 1, and R at 100. This corresponds to recall, to top 1 and top 100 recall. Then we have 3 categories. So first is non-editorial distortions. So basically, it means that we evaluate this image attribution pipeline on distortions which are benign in some sense, right? So benign in the sense that it could be like a small crop or a small rotation of the image, right? So it's kind of small non-adversarial changes, right? So this is the first thing that we apply. And then depending on whether we have no attack or L-infinity adversarial attack, we also add an adversarial perturbation on top of this benign distortion. So this is the first category. The second category is editorial manipulations. So essentially this is kind of photoshopped images. And there is a data set which is called PS Battles. So it's an open source data set with photoshopped images. I think this is really nice and probably underexplored benchmark for for this kind of security oriented adversarial robustness tasks. And editorial plus non-editorial means that we apply essentially this benign non-editorial distortions like small crops or rotations on top of photoshopped images. Okay. Here we have four methods which existed before in the literature. So it's either standard supervised learning on ImageNet, right? So we can just use the model from PyTorch Vision, right? And it already produces some meaningful embeddings, right? So we can just use that potentially, right? But you can see that even without any attack, the recall under the small distortions like crops and rotations is not that great. So it's around 20% or 40% if we measure recall at 100. So for editorial manipulations, it is better. But yeah, if we apply both of them, then yeah, it's not that great. Okay, then we also benchmark deep augment plus OcuMix. So these are methods to improve essentially robustness to distribution shifts. Then we also benchmark robust supervised baseline from robustness library. So this is, I think, probably one of the most well-known open source models trained on ImageNet, which is robust to adversarial examples, at least to some extent. And we also benchmark an undefended contrastive learning model, which was trained on PS Battles from the previous work of from Adobe. Okay, so basically the main finding is that, okay, the existing models are not robust and not too accurate, right? So we can see that under L-infinity adversarial perturbations, right? So yeah, so maybe we can actually just look at the last column. So maybe this is probably the most representative one. So basically we can see that, yeah, that under adversarial perturbations, all the models fail. And I want to emphasize that these adversarial examples are saved as valid JPEG files, right? So if somebody really uses, I don't know, a standard model from from Torch Vision library to produce these embeddings, then yeah, it's really possible to fool these models and fool very easily, even if the image is distributed in JPEG format, right? So this is kind of quite concerning, and yeah, so and even standard PGD attacks are sufficient to reduce the recall to 0%. So we don't need any advanced methods. Okay, so this is a set of our new models that we trained. So I think they are pretty well performing. So the first one is undefended contrastive learning model, trained on Behance 100 million. So essentially, this 100 million of images from Behance. So why Behance? Because Behance contains both photographs and also some artwork like posters and so on. So it's quite diverse data set. So it's good for for general image attribution, because I think standard ImageNet is biased quite a bit towards photographs, right? So and it has only few artworks. And basically what we can see is that that our robust training significantly improves adversarial recall. So if you take a look, then basically all the numbers are, let's say, pretty high, right? So 90%, or okay, if we consider top one recall, then it's like 80, like which one is the best model? So maybe, I don't know, let's say trained with Epsilon 2. So it has 87% top one recall, and something like 63 under adversarial examples. So this is pretty much better than standardly trained models. And another interesting thing is that that our adversarial training improves even the standard recall on editorial manipulations. So I think this is okay. So let's try to understand this claim. So basically, what we observed is that if you consider the performance, like top one recall on editorial manipulations, this 88.6 for the standard contrastive training, right? With adversarial training, we improve the performance, like the standard performance on these photoshopped images, right? So just by doing essentially L-infinity adversarial training, we are becoming more robust towards this Photoshop changes, right? So I think this is quite remarkable, because it kind of says that adversarial training can be useful also for something else, right? And this something else is essentially that the model becomes more robust towards this kind of this photoshopping or this kind of fake image manipulations. Okay, so I think I have something like 7 minutes probably, right? So until 5:45. Okay, I will try to be quick. Okay, so I wanted to share a few plots, which I think are most interesting from kind of the perspective of machine learning, than more than from the security point of view. So essentially, one issue with adversarial training in image classification that we know from the literature is catastrophic overfitting, right? So basically, it is well illustrated actually here. So this is the plot of recall of standard and adversarial recall over the training epochs, right? So we train the models using essentially a different number of PGD steps, right? So basically all three models are adversarially trained models, just with different number of PGD steps. And we can see that with one step of PGD, so this is what is known as FGSM, fast gradient sign method, training here also leads to catastrophic overfitting. So this is kind of very similar to what happens on image classification, right? So, but at the same time, PGD with 2 steps is totally fine and does not lead to this kind of oscillating behavior, as you can see, like for the blue curve, right? So this kind of the catastrophic overfitting behavior, when suddenly, like in one epoch or even less, we have a complete drop in terms of the adversarial robustness, right? So this is a problem that has been observed in image classification, right? And essentially the lessons from image classification are totally applicable also here for image retrieval model, right? And it's something that is nice to see that the lessons from there are actually generalizable, right? So and then basically, the simplest solution is just to increase the number of PGD steps to, I don't know, from 1 to 2, and this is kind of totally resolves the problem, right? And having 2 steps of PGD in the training loop is still leads to tractable training. So this was quite nice to learn. The second one is robust overfitting. So what is robust overfitting? You can see it on the green curve. Okay, so first of all, so the 3 models correspond to essentially to different epsilon used for training, And at the same time, we fix the epsilon which we use for evaluation. So for evaluation, we use epsilon 8 over 255, and we train 3 models with different epsilons. Essentially, what we see for the green curve is that there is a peak performance, which is achieved around epoch 8, I think. And then we start to see overfitting in the sense that adversarial recall goes down, right? So yeah, so this is interesting because it basically says that if you don't monitor your progress over epochs, and if you just take the last model, then the last model is going to be very suboptimal, right? So you need to combine this procedure with early stopping. Otherwise, you're going to get actually something like 10% worse performance, which is really significant, right? So again, it's very similar to what happens in image classification. So it seems to be a very general phenomenon, and I don't think that we have actually a good understanding about why it happens in the first place, right? So I think kind of more research is needed to have some, I don't know, theoretical foundations about why this essentially why both catastrophic and robust overfitting occur. But it was interesting to see that the same lessons that we saw in image classification are also applicable here. Okay, so I have 3 minutes, so I will try to quickly go through this. So okay, so what is here is like, okay, now we switch gears a bit and talk about hash inversion attacks. Okay, so what it means? It means that we take a hash of an image, so hash or an embedding, and visualize the image, which is a result of its inversion, right? So we invert an image embedding and see what is the what are other images that can lead to the same hash. And the goal of the attacker in this case can be to compromise the validity of this hashing model. So there was a case last year with Apple and their neural hash model. So I'm not sure how many of you have heard about this case, but essentially, in summary, Apple wants to track some completely undesirable content, right? And for this, they kind of uploaded models on every iPhone and every MacBook, basically that essentially does exactly the same task. So like image, like okay, not exactly the same, but it tries to map. Okay, so it tries to compute an embedding of the image and then to map it to the database of undesirable images. So essentially, it's kind of the same task, but for a different goal, right? And yeah, and then basically the concern of that for that model was that the model didn't really make much sense, in a sense that the inversions of the hashes were completely not meaningful, right? And then people started to question, okay, whether it's a good model and whether Apple knows what it's doing and so on. So that was, I think, quite undesirable coverage in the news for Apple, and also it's totally valid question, like what is this model doing, right? Okay, so I will show you some pictures. So you have some target image, and imagine that we start this inversion process so that we invert the hash of the model, so of the image. So imagine that the model outputs that this is the hash of this nice camel image, that is 01001. And then we start inversion from some random image, and then we converge to an image which outputs exactly the same hash, so 01001. But it really looks like still like completely, Gaussian noise, right? So it does not really have features of the camel, right? So this is kind of concerning, right? Because I mean, so it was exactly the same case with the neural hash, that people did this and say, okay, the model doesn't make any sense. Yeah, but actually fixing adversarial vulnerability gives us a chance to fix this attack as well. So there was prior work on this in terms of image classification. And again, we wanted to see whether the same lessons generalize to image attribution as well. And basically the answer is yes, that for standard model, we have this kind of inversions, right? So they really look like unstructured noise. And if we train models with our robust contrastive learning objective, then if we train with epsilon 2, we start to get much more meaningful shapes of the inversions, right? And you can also see that here, for example, camel is mirrored, right, compared to the original image. And this is also expected because like this mirroring augmentation is one of the augmentations that was used to train the model. So it's totally expected that the model should not distinguish, like mirrored images, right? So this is kind of one of the invariances that the model has been trained with. And we can see that the more robust we make the model, so if you train it with a larger epsilon, the more shape bias the model has. So I think this is pretty nice because it generally improves the trust in the model. So okay, so I don't have any more time. I realize that, so I will go slightly over time, like a couple of minutes. I'll just mention what we did here. So there's also this robust image, so this image comparator part which basically outputs a heat map, like about which part of the image has been adversarially, well, not adversarial, but just like, let's say, photoshopped, right? So about the editorial changes. And we basically show that this model can be also made robust. So basically you can make the whole image attribution pipeline robust, not just its parts, right? So, but yeah, more details about this in the paper. Yeah, and this is the final slide. So yeah, so I think, yeah, we have some interesting messages. I hope, I mean, maybe they are well known for some people, but I think we were kind of quite surprised in some aspects, right? Okay, so the first thing is that current state-of-the-art image attribution models are non-robust, right? This is, I think, already not so trivial, right? Because the model, like, is the whole pipeline, right? Which has kind of 2 stages, right? And then you have this requirements that the adversarial examples should be realistic in the sense that JPEG should not kill them, right? So it's not kind of clear in advance that this kind of model would be non-robust. The second part is that, these attacks are fully realizable in the sense that the attack is applied in digital format and not in the wild where it's captured by camera and so on, right? So it's really much easier for the attacker. And also the attacker is supposed to have white box access to the model, right? So this is, again, this is not the case for all the applications, right? For example, if you want to fool, I don't know, the copyright system, like copyright detection system of YouTube, right? Like the model is not available, right? So you cannot really do white box adversarial examples, right? So, and this kind of security by obscurity could be a good strategy actually, right? So there, but here, if we deploy these models like the Snell hash model, for example, to edge devices, and so the model is just lying somewhere on the disk, right? And then you can just take it, and with a little bit of reverse engineering, you can extract the weights, right? Which somebody actually did for that model from Apple, right? So this is kind of concerning, and this creates this kind of realistic threat model. The third point is that we don't, okay, this is our opinion, so maybe we can discuss this, but so I think we don't necessarily need adversarial robustness in every application, right? So I think it's more like we need it in critical applications where this kind of bad actors are engaged, for example, in something like disinformation campaigns, right? So, and we know this especially for the last years. There's so much disinformation on social media, like with COVID, with wars, and so on. So it's really important to preserve trust in online information, right? So like you have this kind of check marks, like verified accounts in like on Twitter and so on, right? So this is kind of the first step, but I think, yeah, machine learning can play like larger role in kind of verifying the content and the provenance of this content. Okay, and the fourth point is that improving robustness is possible. I mean, it is possible, right? But it requires specialized training procedure, right? So it does not come for free, right? Even if you have lots of data, right? It still does not come naturally, right? You need to change your optimization objective to essentially something like adversarial training in order to make the whole image attribution pipeline robust. Okay, that's it. I think I was over time for like 5 minutes, but I think still 10 minutes left, so I think it's not too bad. So thanks a lot for your attention, and I will be happy to answer all your questions. Okay, so I think yeah. So I see one hand raised. Antonio, yes, please.
Okay, thank you, Maksym, for the nice presentation. Was really appreciated. The question that I would like to ask you is about the threat model. So you're assuming to have white box access to the target model, since you say that we can somehow reverse engineer the model, since it can be stored in some devices. Have you tried to investigate, for example, if, for example, how the performance change when you collect or when you build up a surrogate model and you exploit transferability of adversarial example to targeted model? So have you tried to investigate in this direction? Do you think that you will be able to present the same kind of accuracy, or do you expect like a drop on the performance?
Yeah, so I think this is a great question. So, okay, so what happens if we don't have white box access to the model? So, yeah, okay, so we have not investigated this because, yeah, we assume that, okay, that since the model is anyway going to be according to the standard, I mean, okay, it depends also whether the standard eventually gets implemented or not, but at least according to this standard that is developed, that model will be on the edge devices. Yeah, so it's fully available white box, and some people like have reverse engineered this, like kind of the same model, like the same principle for like this for the Apple mayoral hash model, right? So it's definitely possible to reverse engineer this model. So yeah, so what happens with transferability, we have not investigated, but they're having a lot of works on that, right? And I think the main summary is that, okay, so if you can query often enough the classifier, then you can get quite far with either black box adversarial attacks, right? Or with model stealing, right? So with black box adversarial attacks, I think usually it's something on the order of thousands or tens of thousands queries, right? That you need to essentially to come up with a single adversarial example, which is actually quite a lot, right? So if the model is just on the server, right? If it's like, I don't know, for example, this YouTube copyright detection model, right? If it's on the server, then you don't know anything about the architecture. Then you know, and then if they restrict the number of queries that you that you can make to the model, right? So then it's hard for the attacker to attack this model, right? So, but it's not. I think it's mostly, yeah, it's mostly security by obscurity, right? Because the attacker does not know exactly the architecture, the model, and so on. So, yeah. So it all depends, I think, on yeah, also on the number of queries that you assume the attacker has, right? So if it's something like I don't know, Google Image API, right, which classifies images, I think there you basically have unlimited number of queries, and then you can either steal the model or generate arbitrary adversarial examples. So there it's much easier. So yeah, so my understanding is that you can go quite far if you are unbounded in terms of the number of queries for the black box setting. But if you are constrained in terms of the number of queries, then I think the attacker does not have too much chances without some extra knowledge. This is at least my understanding.
Yeah, thank you a lot, Maksym.
So thank you for the question and answer. Are there any other questions from the Zoom chat? Otherwise, there's a question in the YouTube one. Okay. Antonio. Okay, Antonio has another question, so feel free to go.
More technical question. You say that your adversarial example should survive to the JPEG compression. This is quite technical. How much of the quality do you want to preserve when running the JPEG compression algorithm? So if you have this in mind or not, I mean, it's fine. It was just technical.
Yeah, I think in the paper we used something like from 50 to 100, right? So I think the scale, okay, if I remember correctly, the scale is something like from 0 to 100, and 100 means like the least possible amount of compression, right? And then I think we tested it from 50 to 100, something in this range. And of course, you see that, you know, like at some point you see a drop in how effective are the adversarial examples, right? But I think this drop comes around, I don't know, 40, 30. So this kind of range of, but this is kind of quite quite severe JPEG artifacts already, right?
Yeah,
So,
exactly. Yeah, exactly.
Yeah, I think if you approximately want to preserve the quality of the image, then actually adversarial examples are surprisingly robust even by default, right? But I think it is also important that we, like, in the formulation that we use, we maximize the distance, right? So yeah, so this is the formulation that we use, that so that we don't actually craft adversarial examples on the decision boundary, right? Which are like can be easily flipped to the other side if we change a little bit them further by this JPEG compression. But we really optimize them to be, as far as possible in the embedding space, right? So it's like, okay, there's no decision boundary in this case because it's not classification, but but I think this kind of formulation helps to make them more robust and use kind of the full potential of this L-infinity ball that we have in order to to generate an adversarial example which will be quite robust. Yeah.
Thanks again. Sorry, I'm done with the questions.
Okay, so there is a question from the YouTube chat, which is, does the Photoshop image is considered with level of Photoshop? For example, does changing 10% image with Photoshop needs more robustness, whereas 80% will need less robustness?
That's a very good question. So we have never looked at this. So what kind of examples I have? Let me see. Is there something maybe in this presentation? Yeah, I think maybe these are good. Yeah, so I think most of the changes. Okay, first of all, where all these Photoshop images are coming from. So this is a data set which is called PS Battles, which was collected around 5 years ago. It was collected from Reddit. On Reddit, apparently there is some thread where people try to Photoshop some images, right? And then some researchers from the University of Basel, I guess, have collected it in a data set. And there, most of the changes are quite subtle. Not all of them, but I think roughly, I don't know, 80% of the changes are like, it's only like one small detail is changed. Like, for example, if you can see here, I'm not sure if I can zoom in. No, I can zoom in. But here, for example, on the second picture, it's only one hand, like that is photoshopped, right? In the first image, it is the whole object which is changed, but I think it's not even 10% of the whole image. It's more like, I don't know, 5%, 2%. So it's not a large change, but it's true that some Photoshop changes are larger, but they are more rare. But then, yeah. So the kind of the issue here is also that, yeah, that what is the distribution, the distribution of Photoshop changes that we are talking about, right? So I think it's highly dependent on the, on the content. I mean, it's kind of hard to say that on average, the people change, 5% or 50% of the image, right? So I think it all depends on the application, like, yeah, that you have in mind, right? I mean, so basically what I mean is that, like, I think sometimes like it could be really some very subtle detail, right? Which is changed, right? And sometimes it's a larger area, right? So yeah, but in any case, we want, like as model designers, right? We want to still be able to find the original image despite all these changes, right? So but coming back to the original question, yeah, we have not looked at this, and this would be interesting to quantify maybe how robustness is depends on the amount of the editorial change that we have in the image. So and then maybe I would also add that we know from image classification literature that essentially the data distribution really plays a crucial role in adversarial robustness, right? So so I would expect here, like, also to be important, like what is really, like, I don't know, the distribution of colors, how large is the editorial change, and so on.
Okay, thank you. And I have a question, which is, do you think that to create more robust model in this area, do you think it might be useful to combine a few other technologies like local sensitive hashing, or in general, if there is already some insight that like local sensitive hashing are maybe less accurate but more robust to this kind of attacks?
Local sensitive hashing, you mean to use the embeddings and then hash them? And
yeah, basically what I had in mind is that like the computation of the hash can be like the composition of a lot of like window that you can take on the file, and then you have like something that if you, I mean, you're basically trying to not use the real hash of a thing, which is like something very, very far away. But if you change one of these windows, still the hashes are close. Something like this.
Okay, so basically, okay, so if I understand correctly, like, okay, so essentially, okay, so what I have in mind is that, okay, that if the embeddings are already very far away from each other due to an adversarial example, then if we apply some further hashing on top of them, they will likely to be also far away from each other, right? So yeah, so whatever post-processing we do on this embedding, so if these embeddings are already non-robust, then whatever we do them afterwards will just, you know, preserve this non-robustness, right?
Yeah, you're right.
Yeah, so I think, yeah, I mean, I think it kind of boils down, like, I think whatever we do with these embeddings, it boils down to the, you know, non-robustness of the deep neural network that's used to produce them. And this non-robustness is kind of accumulated over the layers of the network. So yeah, so I think in order to address this issue, then we really need to make, I mean, we really need to use something like adversarial training to make the network itself robust. But yeah, but okay, on the other hand, like I could imagine that there could be some approaches that go along the lines of security by obscurity, right? Essentially that, okay, that maybe, okay, maybe the network is known, but then you apply, like let's say maybe the attacker has white box access to the, you know, to the network, but then on top of it, you have some random transformation of your embeddings, right? So like maybe this kind of LSH, for example, right? Or some other transformation that the attacker does not know about. And then maybe it can be helpful to, yeah, to get some security by obscurity, but yeah, although I think, yeah, ideally kind of, I think what we want is really security by design, right? I think this is something that adversarial training can give you. And also I think for this task, you get quite small degradation in terms of the standard recall, right? So maybe I can go back to the table just to give you some numbers. Yes, for example, here the standard recall, okay, sometimes it's even improved, right? So from 84% to 87%, but yeah, it's either improved or stays on the same level. So in the sense, we get robustness for free here, right? I mean, for free in terms of we don't sacrifice standard recall, but we still pay the computational price that it's roughly 2 times more expensive. So, but I think, yeah, in this application, this seems like a very satisfying solution to.
Like, of course, I can see it really. Thank you for the answer. So, so if there is one last question, otherwise we are done. I assume that. Okay. So.
Okay,
Maura?
go. You can close it. You can close it.
Okay,
Sorry.
it's my turn. So thank you again for being all here today. Thank you again, Maksym, for the great talk. It was very, very a pleasure to like hear about all of your work. And this concludes like the seminars of today. I think that now we can like stop the streaming. And if you have like some